Hi, welcome to this lesson on calculus, the second derivative. Let's have a look at question 5. We're given a rough sketch below of a function f, and we want to determine any stationary points, the intervals of where the function f increases or decreases, and then we also want to know if there's any intervals of concavity and if there's an inflection point. Okay, so this function immediately jumps out to me as a quadratic function, and it has a turning point here, which looks like it has a positive x value and a negative y value. It has a y-intercept at 0 and negative 21, and it's got two x-intercepts at negative 3, 0 and at 7, 0. So I can quite confidently work out what this function looks like. So I'm going to use f of x equals, in the completed square form, a times x minus p all squared plus q. Okay, and because the way the graph is shaped, it's got a minimum turning point and a smiling, I can therefore say my a has to be a positive number. Okay. So first of all, can you see between the x-intercepts lies your p-value, which is always your turning point, lies between your two intercepts. So if I add 7 with negative 3 and divide by 2, I'll get positive 4 over 2, which is 2. So this p-value should be 2 here. So 2 is 5 distance away from 7, and it's 5 distance away from negative 3. Okay, so it's symmetrical. So this is 2. So I've already got my p-value. So f of x equals a times x minus 2 all squared plus q. Now I can find a and q by using the points on the graph. So I'm going to take the points 0 and negative 21. So when I put x equals 0, the y value should be negative 21. Okay, so this is equivalent to saying a times 0 minus 2 is just negative 2. Squaring it becomes 4 plus q. That must be negative 21. So we've got our first equation, 4a plus q equals negative 21. Okay, next I'm going to take f at 7, and if I do that, I must get 0, because that's the coordinate, 7, 0. Okay, so if I do that, I'm going to get a times 7 minus 2 is 5, squared is 25, plus q, and that must be 0. So I've got my second equation, 25a plus q equals 0. Okay, so I have a system of linear simultaneous equations, which I can therefore solve for a and q. Okay, so what I'm going to do is I'm going to subtract equation 2 from equation 1, because they'll get rid of the q values. So 25a minus a, that's positive 21a. Q minus q is 0. And on the right, we have 0 minus negative 21. So that's positive 21. If I divide both sides by 21, I therefore get a equals positive 1, which is what we came to expect. Okay, so therefore, so far we've got f of x equals 1 times x minus 2 all squared plus q. Okay, and lastly, to find that q value, we can just take any other point. So let's take negative 3, 0 if we wanted. So f at negative 3. So if I substitute negative 3 here, negative 3 minus 2, that's negative 5. All squared is 25. Plus q, and that must equal 0, because at negative 3, the y value is 0. So if I solve for q here, I get negative 25, which again makes sense because it's below negative 21. I could have also just substituted the a value here into one of these two equations and also found q. Okay, so either way you do it, as long as you do it logically and correctly and get the same correct answer. Okay, so now we have the full form of this function. That's f of x equals x minus 2 all squared minus 25. Okay, so now we can start answering all those questions on our calculus. Okay, so stationary points. All right, so that is when the first derivative is set equals to 0. So if I expand this function out, I get x squared minus 4x plus 4 minus 25. So that's minus 21 in total. Okay, so let's write that. So the first derivative is then going to be 2x minus 4. Setting that equals to 0 and solving for x, we get x equals 2. And that's what we came to expect. It's the turning point on this quadratic function. That is when this derivative at that point is 0. So the gradient of the tangent line at that point is 0. Okay, intervals of increasing and decreasing. Well, again, if I look at my graph, I can see that the graph is increasing here, right? So mathematically, I should expect x greater than 2. So let's go ahead and solve that. 2x minus 4 greater than 0, that's the first derivative. Well, that implies 2x is greater than 4 by bringing the 4 across. Dividing both sides by 2, I get x is greater than 2. And that's what we expected based on the visuals of the function. So the interval there is from 2 to infinity. And then intervals of decreasing, well, again, I can see visually my graph is decreasing here. So at decreasing, algebraically, that's 2x minus 4 less than 0. So these are the first derivatives, less than and greater than 0. So I get 2x less than 4, divide both sides by 2, I get x is less than 2. So therefore, x is an element from negative infinity to positive 2. Okay, so that's the interval of decreasing, and we can see that visually from the graph that makes sense. Now, what about the concavity? Okay, so let's go ahead and make some space here. All right, so now that we've got all those information points there, let's do concave down first. So that's the second derivative less than 0. The first derivative was 2x minus 4. So therefore, the derivative of that derivative will just be 2. But that's not less than 0. So therefore, f is not concave down at all, because it's 2. 2 is not less than 0. But for concave up, we have f double prime x greater than 0. And 2 is greater than 0 for all x values. So therefore, the graph f is concave up for all real numbers x, because that's what the quadratic is defined on. Okay, and that makes sense. Look at the shape. It's got the concave up shape, and all the tangent lines are below the graph. So the graph is up from its tangent lines. All right, so that makes sense. So mathematically, it's always concave up. Therefore, it will never have an inflection point, because it doesn't change concavity from up to down. Okay, the second derivative will never equal 0. It's always equal to 2. Okay, so that's the interpretation of this question. I'll see you in the next one.